It says going live. Okay, so
Yeah,
I'm curious. Yeah,
That's
so
your channel.
the light from this goes into that, and then you get this
Wait, but it's like reversed.
infinite loop. Yeah, it shows it mirrored while you're recording, but then it'll flip it. I think for anyone viewing it, it'll be not flipped around. So 99% sure. Okay, so that's kind of interesting effect there. That infinite.
Ever done that like mirrors and stuff?
Yeah.
Wait. There should be like a live.
All right. Well, Cooper, you don't need to watch it because you're here, aren't you?
Well, it'd be pretty cool if I could watch it.
All right. So before we go over this, because we're gonna move on today. Was everyone able to figure out the other couple questions? They should have been relatively straightforward. You can plug into the formula we derived. You can just plug them straight in. Maybe let's just double check. Kate, I saw you grimacing. What'd you get for 34?
34, I got 4v over 3.
Agree? 4/3 v. So it makes sense. If you went out going speed v, and then you came back coming double speed v, turns out that the average speed is 4/3 v. Did you just plug into the formula, or did you figure out some other way?
I plugged it into the formula.
Great, that's perfect. That's what formulas are for, right? So, so the formula we derived was, did you use the second one where it was like
2 times v1 times v2.
So in this case, our V1 is this capital V, and our V2 is this 2 capital V. So if you recall from the other day, it was the formula we wrote was 2V1 V2 over V1 plus V2. So just replacing V1 with this expression, replacing V2 with this expression gets us this. And then on bottom we'd have V plus 2V, which reminds me of one of my favorite theorems. Only some of you guys know about it. Taylor doesn't know. She was in my class last year. Taylor, do you know? I have a really difficult puzzle for you. What is 1 banana plus 2 banana?
1 banana plus 2 banana.
Make
3 banana.
3 banana, yes. Very good. Okay, so anyway, 2 times 2 is 4, and V times V is, maybe let's keep it as V times V. I mentioned that because look, I just throws people off sometimes. V plus 2V makes 3V. That's what I was talking about with the bananas. 1 banana plus 2 banana makes 3 bananas. So 1V plus 2V makes 3V. Those cancel out, and there you go. There's Kate's answer, 4/3 V, or 4V over 3. Are we all okay with that? There's a couple quiz questions in that style. So if you're confused, set some time aside to make sure you understand it. Okay. So the famous puzzle. So hopefully you're able to visualize it. What does it look like? That's very good. Right, so they start off 15 miles apart. Maybe they're on bicycles or something. I don't know. Fine. That's not a bad drawing, I guess.
I think it's bicycle.
Thank you.
If you show me that, I'd say that's a guy on a bicycle.
That gives me great confidence. Thanks for saying that. Okay, they're 15 miles apart. And then the fly leaves Albert's shoulder. Oh, but I forgot to label this, I guess. Albert's going 5 miles per hour. This is miles. Is there really no one in here who's like had me show them this question in class before? That'd be a crazy coincidence because I've showed it to a bunch of classes over the years. But like those puzzles we did at the beginning of the year, this one I sometimes throw in there at the beginning of the year. So I just thought there's at least gonna be one person who has seen this in one of my previous classes. But I guess not. Okay, so did I write that right? So
No.
That should be
They're
5.
Oh, they're both going 5. Okay,
Five.
thanks. They're both going 5 miles per hour. Thanks for catching me. Now the fly goes 8 miles per hour, right?
So he's crafted.
Yeah, he's a fly.
No.
Do you think a fly can go 8 miles per hour? I don't know. I have no idea, but this one can. And so the whole time, so he leaves. So as these guys are converging toward each other, the fly goes, pew, pew. And he goes, bounces back and forth and back and forth. And back. So you might go, wait a second, does that mean I have to do some kind of sum? I have to calculate all the, like how long it takes him to make that first trip, and then how long to make the second trip, and then how long to make the third trip. Does that make sense what I'm talking about?
Yeah.
You can do it that way. There's like a famous, probably apocryphal story of John von Neumann solving it that way in his head at like a dinner party or something. But anyway, there's a simple method. The story goes that some guy tells him the puzzle, and von Neumann thinks about it for a few seconds, gets the right answer, and the guy goes, dang, I was hoping you didn't know the simple trick to solve it. And von Neumann says that he solved it like by doing an infinite sum. But anyway, von Neumann also had a cool idea about this self-replicating robots that would devour the entire Earth, but that was also pretty interesting. Does anyone know the trick? Come on, Julia. What's the trick, Julia?
So you figure out how long it takes for them to meet,
And
then you figure out how long the fly can fly during that time.
Beautiful. So let's do that. So exactly what Julia just said. So she said, figure out how long will it take to meet. Now, why is that relevant? Because that's how long the fly is going to be flying for.
Yeah.
So if we know how long the fly is flying for, and we know how fast the fly is traveling, then we would then know how far the fly had traveled. So the total time involved here would be the total distance, so 15 miles, divided by their combined speed, right? So what's their closing speed?
10.
10. So they're going to be riding toward each other for 1.5 hours. Decent bike ride time. And then the distance the fly travels would be the fly's speed times the amount of time he traveled for. So what was his speed? 8. So 8 miles per hour times 1.5 hours gets us 12 miles. Yes. There's the answer. Cool beans?
Yeah.
Okay. No questions? Sure. So Bob usually walks from his house to the river at a constant speed and then runs home at double that speed. Today he walked out at his usual speed but ran back at triple that speed. If his usual total round trip time is t, what is his total round trip time today? So I want to show a method that will come up a lot in this class, which is if you're not really sure how to proceed, sometimes it helps to just make up values and see what happens. Okay. I hope you'd agree that this question is like the way it's phrased. It's like we have no information, right? We don't know how far away his house is, that kind of thing. Is that making sense? So let's try making up some information, see what the answer is, and then compare. So does the plan make sense or not really? So just to reiterate, the plan is, say I make up a scenario, I make up a distance and a speed and stuff, and I figure out that, okay, under that scenario, the time is, say, 2 hours. And then I change it from doubling to tripling, and let's say it just turns out that now the time is 1.5 hours. Well, that would tell me the ratio between the t's, right? It would tell me that it's 3/4 as big.
Yeah.
Okay, getting blank stares. That means it makes sense, right? Hopefully, when you see it, it'll make sense. So, okay, so let's try it this way. Because this method, guys, I should help you a lot in this class if you're having trouble with doing it just with symbols. Who's got an idea for like a nice distance to use? 10's not bad. I was thinking of a more divisible number. Because we're going to be dividing, huh?
20. Yeah.
Well,
Something like 12, something like 12, or maybe even 24, something that's highly divisible. Because I'd like to work with integers, and I know I'm going to be dividing distance by velocity. Does that make sense? So let's do something like 24. So let's say he is 24 miles. Make it 24 meters. Make it 24 nanometers if you want. Just make him a really tiny being. Right? That makes sense. The size of the units don't matter. So, okay. So let's say he usually goes at, I don't know, what speed should I pick? You want it to be 4? Okay, I like that. Let's say he walks 4 miles per hour. And then, so then what would he return? How fast would he return if we're following this?
8 miles an hour.
Very good, 8 miles per hour. Okay, so that's scenario A. So how long does this trip take then?
Well,
Yeah.
No.
6
Yeah.
plus 3 make 9.
Is that the banana?
Yes, 6 minutes plus 3 minutes. 6 hours plus 3 hours. Are we all okay with that, guys? We sure? All right, so it takes 9 hours. All right, now let's see what happens. Just because, love you guys, I'll color code it to make it extra good for you. Okay, so now, same distance, right? What are we changing now?
the return speed.
Yeah, so he still is going to go 4 miles per hour out. Man, don't we appreciate Kate for coming up with that great? Oh man, everyone's going to be integers. Isn't that just amazing? Like, okay, now when he comes back, how fast is he going?
12.
12.
Wow.
So now how long does it take?
Um,
6 plus.
2.
Now it's 8 hours. So this is the last logical leap that might be a little challenging. What is the answer to the question? What?
8/9.
Very close. 8/9 t.
8/9.
So you gotta come back to the original. Let me call this like T2 and this T2. So the way this question's phrased, please let's address this if there's any confusion, because on your quizzes, there's a lot of questions. They're typically not this. They could be this. They could be on the same level of challenging. But what do you guys think of this method of making up numbers?
Right.
No, Taylor.
No.
Do not like. Well, maybe maybe sleep on it. It's a very strong method. It's very powerful because to solve this question just purely symbolically is doable, but it's very, very challenging, I think. Whereas, you guys see the logic of like, either this method has to work by making up numbers, or the question has no solution. That might be less obvious. Because if changing the distance changes the answer, or if changing the initial speed changes the answer, then the question's not solvable, is it? Okay, hopefully that makes sense. You can try it out yourself if you want to say, I don't know, try doubling the distance or changing the speeds around and confirm. Do you always get 8/9? Is it always an 8-to-9 ratio? Take the dead silence as basically a thumbs up, hopefully. Okay, so now do you see why the answer is 8/9 t?
Yes.
If this time was called t, then this time is 8/9 of that t.
No.
Okay, let's move on. Okay, moving on.
I get it. I got it.
Okay, hopefully we got it. I know it's hard with the I guess I rely a lot on like looking at people's faces, but it's very hard to tell now. I just see a lot of like. Okay, so graph time. Okay, so this is another thing that for a physics class, this stuff comes up a lot. A graph of position versus time. Pretty soon, we're going to start doing ones that have like velocity versus time, things like that. But for now, we're just going to be position, time. So before we do any calculation or anything, in your head, can you picture what this is describing? For our purposes, imagine the particle is just traveling along a one-dimensional track. So just a straight line, okay? Like the number line, right? Imagine the particle is traveling along the number line, right? The real number line. I found there's some misconceptions of this. Sometimes people think that this is talking about a particle moving up a ramp. That is incorrect. Don't think about that. This is just describing, so it's describing a particle moving along one dimension. And at time 0, where is he? Position 40. Almost like mile markers on the highway, right? Oh, he's at position 40 meters. M stands for meters. Where is he 5 seconds later? He's at position 120 meters. So how far did he go? 80. So what was the particle's displacement? 80 meters. Part B, what is the particle's velocity at time 3? Who thinks they know the answer to this one? For $1 million. For 500 bits. Food for thought. What kind of motion is this? How would you, if you had to describe his motion, would you say that he was like abruptly changing speeds?
No.
Nope. He's going the same speed the whole time, right? Huh?
To go off the slope.
Yes, it's a slope. Exactly. That's correct. It's just a slope. So this comes up a lot too. Well, I don't know exactly what's the y value there. That's the problem. Do you have to know the y value there? No, because the slope of this line is the same everywhere. So what this graph is describing is a particle traveling 80 meters over 5 seconds. So my velocity over the entire time period at any given time would be the total displacement over the total time period. So it would be 80 meters. Oops, got ahead of myself. Sorry. Very funny, very funny. 16 meters per second. Are we confused, or does this make sense? How fast is 16 meters per second? Who can run that fast? Anyone? No one can run that fast.
Not me.
I mean, I can.
No one else.
Maybe on.
Don't you ski that fast?
Oh yeah, you can ski that fast.
Just up here.
It's just that's too fast to run. Well, I wonder for someone like Usain Bolt, I wonder if his peak speed, because he goes 100 meters in 10 seconds. So that's an average of 10 meters per second, but he's has to speed up. So I would be surprised if his max speed is. No, I don't think it would get to 16, but something a bit higher.
13.
Huh? Try Googling it. Colin, Google it. What's Usain Bolt's top speed in meters per second? Okay, part C, what's his position function? His position is, let us know what you find, Colin. Starting position plus velocity times time. Do you have any questions on that formula?
It's 12.428 meters per second.
Yeah, pretty fast. But yeah, not quite 16. That makes sense. I was suspecting it was going to be like not a ton bigger than his average speed over the whole race because he speeds up pretty fast. So, questions? No? Okay. All right. For this one, again, we're considering a particle constrained to move along the x-axis. Draw a position versus time graph that matches each of these descriptions. So think about that. And I'll just remind you here. So average velocity. What's the key difference between velocity and speed? Yep, one's distance, one's displacement, which means maybe a shorter answer is velocity can be negative. So with velocity, we care about direction. Okay. So, if I'm moving this way, my velocity could be like -1 meters per second. If I'm moving this way, my velocity is +1. But in both cases, my speed is just the positive. Okay. So, let's see. What does it mean if your average speed is equal to your average velocity? First, this is how you label it. You go time, position. Well, something like this. Now, why is that? Why would our average speed be equal to our average velocity there?
It's not great. Like,
Well, because my displacement's positive. So if it helps you to make up numbers, go for it. You could make up the numbers. You could say, I don't know, my time interval could have been like, say, 4 seconds. And I could have traveled 40 meters. And then do the calculation, you would have got 10 meters per second for velocity and for speed. How about this guy? Just some way that they're not equal. Maybe you maybe you guys can think of one. Can you think of a simple example? I've performed it for you through the art of interpretive dance before.
yeah, like when your velocity is like 0 or negative, then your average speed is not the same.
Yeah. So one way is to that classic example is like, here you go. There you go. It went up and then it went down. Or if you're on an x-axis, what if I go forward and then backward? So what if I went like this? Do you see how in this case, my average velocity would be 0 because I started and ended with the same position?
Yeah.
Okay. Whereas my average speed is some positive number. Okay. So that's one of many possible examples. There's a bunch of different ways you could do that. Okay. For C, it says they're not just not equal; they're precisely opposite of each other. The way I drew the axes might be a bit of a hint to you. How could the average velocity be exactly the opposite of the average speed? If you're just moving left. So if you just go to the left, which would look like that. So say I go from position 0 to position -1, right? My average velocity was negative, but my average speed was positive, but they're the same number. And then lastly, this says that the size of the average velocity is less than the average speed. You could definitely do that. You use the same example pretty much. Does that make sense? So you could have or even maybe a different example would be like that. Say that was my position function, position time. My displacement is that amount, right? And so the overall size of my average velocity would be smaller than my average speed. All right. It's Wednesday today, so I think at this point, I don't know, we can have a little bit of homework, I think, because these questions should be pretty easy. If you're not finding them easy, I would like to just touch base with me for 5 minutes tomorrow, maybe. You might if you're having trouble with them, you might go, there might be just something you're not realizing, and we can talk about it, and it'll be like, oh yeah, it makes sense. So just real quick, how do you find position on a graph like this? On a position time graph, how do you find the position at, say, time 1?
You look at one and go up and then go up.
Yeah, you just look at the graph, it's 90. Easy peasy, right? How do you find velocity at a given time?
That'd be slope.
It is the slope, the slop, okay? How do you find speed?
That's slope.
What? It's slope, but you just always make it positive.
Okay.
That's all speed is. All speed is velocity, but I can say, if you want a mathematical statement, it's speed is just the absolute value of velocity. That's literally all it is. That's all it is. Okay. How do you answer a question like D? At what time or times is the particle located at position 120? How do you figure that out?
Just
Go up to 120, yeah, and then what?
go across.
Maybe kind of visualize this line across and say, at what times did we actually hit that position?
Go down.
You can tell because of the slopes that it's going to be exactly halfway between 1 and 2, so 1.5, 5.5. These last couple might be slightly more challenging, but what is the particle's displacement from 0 to 7? Can I hold on this? Let's see it scroll over a little bit. 60. Very good. Very good. Everyone see how we got that? You sure?
Yes.
So you take its position at time 0, which is 30. Take its position at time 7, which is 90, and just subtract them. That's all you got to do. 90 minus 30. Now, slightly more challenging would be, what is the total distance traveled from time 0 to time 7? This one's going to be a bit more involved.
You get like 30 to 120.
So he did 120 on this first little leg here. He did 120. How far did he move during this time interval here?
Zero.
He didn't move at all, right? He stayed at 150.
Yeah.
And then what did he do? He moved backward 60, right?
So it'd be
It was a 180. So his total distance travel, he went forward 120, then he came back 60. Okay? Which tells you, that shows you his displacement, right? If you go forward 120 and then backward 60, your overall displacement is 60. So, and then, okay, with those two values, how do you find his average velocity? Average velocity.
you just slope. You just see
Go back to your original definition. Average velocity is displacement over time. What was his overall displacement over this interval? 60. The time was 7 seconds, and so whatever, I don't know, use a calculator. It's going to be 8 point something, I think. What'd you get, Kate?
8.57 meters per second.
Okay. That should make you feel good if you're concerned with, if you want things to be easy. Because that graph was kind of complicated, but finding the average velocity is pretty simple, right? Once you do the overall displacement, you get to ignore everything, which is kind of amazing. But okay, how about average speed? How do you find average speed? Total distance over total time. What was the total distance traveled in this problem from 0 to 7?
180.
180. Divided by 7. So what do you got? 25, 26? What do you? 25.71 meters per second. Now, why is this so much bigger than this?
The velocity is like how far away you are from the start point, like at the end. If that makes sense. Like the speed.
There's a, I think I know what you're talking about, but there's a simple answer. Why in this graph is the average speed so much higher than the average velocity? It's because of that. Because we went backward. When you go backward, you're taking away displacement. You're subtracting from the displacement. So you're basically, this whole time you were decreasing the overall average velocity, but you were increasing the average speed because you were moving.
Where do you want us to get?
Let's finish it. So they should be, I hope, pretty straightforward. We're gonna have our first quiz. Maybe we'll make it a take-home quiz. I'm not sure. We'll think about it. But anyway, let's end the stream here. So end stream.